No, okay. Let's review a little bit. If my original function is increasing, then my derivative is positive. And if my original function is decreasing, my derivative is negative. And when f has a max or a min, f prime is equal to 0, or it could be undefined. And there should be a sign change also. Critical points are interior points on a function at which f prime equals 0 or undefined. Or another way to say that is the tangent line. The tangent line could be what? If my slope is 0, then my tangent line is horizontal. Or if my slope is undefined, my tangent line would be vertical. So f prime gives us information about the slope of f. And that implies that f double prime, the second derivative, gives us information about the slope of f prime. But it also, here's what we're going to add today, it also tells us about the concavity of the original function f. So if my second derivative is positive, then my function will be concave up. It will open up. And if my second derivative is negative, my function will open down and the concavity will be negative. So we have what's called an inflection point, and an inflection point is a point on a function at which f double prime equals 0 or it is undefined and changes signs. And so an inflection point is a point in the original function where f of x changes concavity. So let me illustrate that. Let's say I have a function here. And at this point of the function opens down, so it is concave down. At this point, the function opens up, so it is concave up. And so since it opens down here and opens up here, at some point it changed concavity, right? Let's say it switched maybe right there. This is called the point of inflection. The point of inflection is where it changes concavity. Well, there are a couple of ways to describe the point of inflection based on the information that they give you. So if I have the original function, I'm going to look at where it changes concavity. But if I do not have the original function, let's say I have the first derivative, I could say that a point of inflection is where it changes from increasing to decreasing or decreasing to increasing. So it's where my derivative changes from increasing to decreasing or vice versa. And if I have the second derivative, I can say the point of inflection is where the second derivative equals 0 or undefined, and it must change signs. So I see a question like this fairly often on the AP exam. So this is something that we need to know. If your function is concave up, the tangent line will be below the function. And if your function is concave down, then the tangent line will be above the function. So if it's below, it's going to be an underestimation. And if it's above, it's going to be an overestimation. And the reason that is true, let's look at this graphically. Okay, let's say I have a function that is concave up. And I draw in a tangent line at this point. And then they might ask me, I want you to estimate what this point is. Well, this is what it actually is on the function. And my tangent line is obviously below that. Therefore, this will be an underestimation of what it actually is, because the function is concave up. And if the function is concave down, then my tangent line is going to be above what the function actually is, and therefore it will be an overestimation. That makes sense. Any questions for me so far? We've added the second derivative, which talks about the concavity. A point at which a function changes concavity is called a point of inflection. And that is really all that we have added so far. Okay, so let's look at a couple of examples. And so I apologize for the formatting here. It kind of got messed up a little bit, but this is my original function. This is my derivative, which should be over here. And this is my second derivative. And you can see, okay, it works out nicely. Like my original function looks cubic, and then my first derivative is 1 degree less, so it's quadratic. And my second derivative is 1 degree less than my first derivative, so it's linear. And so what I'm going to do is describe certain things using all three of these graphs. So let's talk about, first of all, where my original function is concave down. Okay, so I'm going to say f is concave down. Let's go over here on this interval. This is my original function. I'm looking at where my function opens down. And let's say it goes from right here all the way to somewhere right in here. Let's call that, like, I'm estimating, right? But 2.5. So I can say that from 0 to approximately 2.5, my original function is concave down. That makes sense? You all good? Well, I could do the same thing using the graph of the derivative, but it would be stated in a little bit different way. Here, I would have to say f prime is decreasing. Because look, this is a graph of the derivative. I've got a negative slope from 0 to approximately 2.5. If my slope is negative, that means the derivative of the derivative is negative. And therefore, it would be concave down, because my second derivative is negative. And so what I'm saying is that f is concave down and f prime is decreasing mean the exact same thing. They both mean that my original function is concave down. It's just this is stated in terms of the original function, and this is stated in terms of the derivative. Well, I could also state it in terms of the second derivative by saying f double prime is negative. So all three of these things say the same thing. And I've given the interval on which they are true. Looking at the second derivative here, My second derivative is negative from 0 all the way up to approximately 2.5. Not exactly, it looks like on that graph, but it's close. Okay. And so all three of these things say the same thing. Well, let's go to f is concave up. It's going to be concave up on the interval from, let's say, 2.5 to approximately, let's say 5.5. Or another way I could say that would be f prime is what? Is increasing. Or another way I could say the exact same thing is f double prime is positive. And so these three things mean the same thing. And so depending on which graph you have, you might be asked questions and you might have to frame it in a little bit different, but it's all relating to the same concept. Okay. Well, let's look at another example here. It says use the graph of f of x to estimate where. So it is important when you are working these problems, label what they give you because so that you do not get confused. And also, I don't know why, but one of my letters is missing there, so that should be a D. So let's go through these. This is the graph of the original function. And so f prime of x is positive whenever the original function is increasing. Or another way to say that is I have a positive slope. So looking at my graph, where do I have a positive slope? Let's say from like, let's go to negative infinity all the way up to A. And then over here, it would be from B to positive infinity. Well, f prime is negative when f is decreasing, or I have a negative slope. So looking at my graph, where do I have a negative slope? From A to B. Well, f double prime is positive when my original function is concave up. And where is my original function concave up? From D to positive infinity. And f double prime is negative when my original function is concave down. And looking at my original function, that would happen from negative infinity to D. So now, f of x has critical points. Again, what does it have a critical point? When the derivative is 0 or undefined. My derivative is not undefined here because there are no cusps or corners. It is equal to 0. So it's going to have a critical point at x is equal to A. And there's another one at x is equal to B. And that is because my first derivative is equal to 0. And f of x has an inflection point. It's where it changes concavity. So that's going to happen at x is equal to D. And that is because my second derivative is equal to 0. And it changes concavity from concave down to concave up at D. All right, well, let me pause right there for just a second. and give you an opportunity to ask me any questions so far. And I think I need to tell a calculus joke of the week also in just a second. So any questions?
Is C anything?
It is not, no,
Okay,
at this
just
point.
there.
I mean, it's concave up at CE,
Yeah.
but no. In terms of a point of inflection or a critical point, no, it is not anything. Okay? Do you know how a mathematician differentiates in the jungle? With Amazon Prime. That's kind of funny, right? I mean, come on. I made up a joke, a math joke the other day. How does a mathematician differentiate in the jungle? With Amazon Prime. You gotta give me something, right?
How does deriving and Amazon Prime have anything to do with it?
Jungle.
Because it's F prime.
It's F prime, Shelby. If I have to explain my jokes, they're not really fun. I know. Well, I can tell bad jokes and it can be so bad that it's funny. But then if I have to explain the bad joke,
And it,
that just takes away all the funniness.
okay, I think I understand it now.
I think I'm going to move on, right? Because
Just act like you didn't have to explain.
we're not doing so well. Rewind. It's like your GPS, you know, you take a wrong turn, and you're like recomputing, right? We are recomputing. All right. Well, in that example, we had the graph of the original function. Here, we have the graph of the derivative. So label it so that we do not get confused. And let's look at the questions here. It says, when is F increasing? When is F decreasing? Justify your response. So F is increasing when F prime is positive. Everybody agree with that? Yes? My original function, which I don't have, but my original function would be increasing whenever the derivative is positive. And so looking at this graph, this is a graph of the derivative. And so it will be positive whenever the line here is above the x-axis. So therefore, it would be from -4 to +1. Everybody okay with that? When is it decreasing? F is decreasing when F prime is negative. And looking at my graph, my derivative will be negative whenever my derivative graph is below the x-axis. So therefore, it's going to be negative from 1 to 4. And part B says, determine the x-coordinates of all extrema, justify your answer. So how do I have a max or a min, an extrema? It has to be either a critical point or an endpoint. Okay, so extrema occur at a critical point or an endpoint. And a critical point is where F prime equals 0 or it's undefined. So let's look at the critical points first. And there is a critical point at x is equal to -2 because my derivative graph is equal to 0. It touches the x-axis. However, they ask for extrema, and I would say there is no extrema at x is equal to -2. Why not? It does not change signs. Go back to what we said originally. F is increasing on the interval from -4 to 1. So let me just draw some random graph, right? It goes up like that. and -2 is in the middle there. Is there a max or a min in the middle? No, there can be because it's increasing the whole time. Okay, so there is no extrema because f prime does not change from positive to negative or negative to positive. So since there's no sign change, there is no extrema at -2. There is, however, an extrema at x is equal to 1. What is it? Is it a max or is it a min? Well, it has to be a maximum. Here's one. Go back to what I said. F is increasing on the interval from -4 to 1, and then it is decreasing from 1 to 4. So look, the function is increasing, it goes up, and then when it gets to 1, it goes down. So there has to be a max at 1, and you can see that because on the derivative graph, it's crossing the x-axis from positive to negative. So x is equal to 1, f prime changes from positive to negative. Therefore, there is a relative max at x is equal to 1. But I'm not done because an extrema can also be at an endpoint, so I need to check my endpoints. So let's do that. So I've got x is equal to -4, and sometimes students can get confused on this, but you really shouldn't, okay? But I think that they get confused because they are looking at this graph, but you have to keep in mind that this is not a graph of the original function. This is a graph of the derivative. And so I know that at x is equal to -4, it is a local minimum. It doesn't look like a minimum there though, but it is. And here's why. Go back to what we originally said. F is increasing on the interval from -4 to 1. So look up here. It starts at -4 and then it does what? It goes up. Right? Therefore, -4 has to be a minimum. So x equals -4. F prime is positive just after the endpoint therefore x equals -4 is a relative minimum. Well, what about the other endpoint at x is equal to 4? Is it a max or is it a min? It's not. It's a minimum. Why is it a minimum? Look, f is decreasing on the interval from 1 to 4. So look up here. It starts at -4 and it goes up. And then at 1, it starts to go down. And then it stops at 4. So what is it? It has to be a minimum because my function is decreasing right before the endpoint. So f is equal to 4. F prime is negative just before the endpoint. Therefore, x equals 4 is also a relative minimum. So we have managed to go through half of our class, and we really haven't done any math yet, right? So it's kind of like we're in stats or something. So Aubrey complains all the time. last year. So we need to do a little math now. All right. Here we go. Example 3, determine any extreme values of the function f of x is equal to negative 2x cubed plus 6x squared minus 3. Additionally, determine the concavity using the concavity test. Probably didn't even know there was a concavity test, right? Nevertheless, here we go. So let's take the derivative. We got negative 6x squared plus 12x for my f prime. So my first derivative is quadratic. Are there any holes and asymptotes? No. Thank you. There are not. So I do not have to worry about when x is undefined. Is my function bounded? No. So there are no endpoints. So the only way I could have a relative max or min is when my derivative is equal to 0. So I'm going to set it equal to 0 and solve for my critical points. So let me factor out a negative 6x, and that's going to give me x minus 2. And so that is going to tell me that x is equal to 0 and x is equal to 2. And if I plug these points back into my original function, they both exist. Therefore, I know that these 2 points are critical points. They asked me to find the extreme values, though. So to do that, I need to do a sign chart where I'm plugging into f prime. And I'm going to plug in values around 0 and 2 to get my sign chart. And again, I'm plugging into the derivative because it's showing me increasing and decreasing. So if I take negative 1, for example, and plug it in, I've got negative 1 minus 2, which is negative 3, times positive 6. So that will be negative. If I plug in 1, I've got negative 1 times negative 6, which is positive. And if I plug in 3, that's going to give me negative 18 times 1, which is negative. And so now I can say I have a minimum at 0. And if I take 0 and plug it into the original, it gives me my coordinate point, negative 3. How do I know it's a minimum? The sign chart changes from negative to positive. Therefore, it must be a minimum. And I know that I have a max at 2. If I take 2 and plug it into my original equation, you should get 5. Therefore, I know that I have a minimum. It's going to be the absolute minimum because there are no other possibilities. And my absolute maximum would be at 2, 5. Okay, so up until now, theoretically, we haven't seen anything new. All of that you are responsible for on your quiz yesterday. But now it says we need to determine the concavity. So to get the concavity, we're going to take the second derivative. And so that's going to give me negative 12x plus 12. This is a linear function. Holes or asymptotes? No. Therefore, all I need to worry about is when my second derivative is equal to 0. And I'm going to factor out a negative 12, which gives me x minus 1. I can divide out the negative 12, and I get x is equal to 1. And so x is equal to 1 is a potential point of inflection. And I say potential now because in addition to the second derivative having to be 0, it's also got to, the second derivative has to change signs for it to be a point of inflection. And so I've got to do a second sign chart. And this time I'm going to plug into the second derivative to check my concavity. Okay, so if I pick a value on the left side of 1, let's say 0, I plug in 0, and I get 0 plus 12, so that is positive. And then I plug in, let's say 2. That gives me negative 24 plus 12, which is negative. All right, and so now I know that it is concave up from negative infinity to 1, and it is concave down from 1 to positive infinity, and x is equal to 1 is a point of inflection because f double prime equals 0. And in this case, it changes from positive to negative.
Could you explain how you knew the concave down, concave up part rather than the sign chart?
Yes, I get that directly from my second derivative sign chart. So since my second derivative is positive on this interval, it is going to be concave up from negative infinity up to this point, which is 1. And then since my second derivative is negative on this interval, and I got that by plugging values back into the second derivative. So if I pick a number on the left side of 1, let's say 0, and I plug 0 into my second derivative, I get 0 plus 12, which is positive. Therefore, this is positive. Just like the sign chart that we did for the first derivative. And if I plug in 3, for example, it's going to be negative. And therefore, that tells me that on this interval, from 1 to infinity, my original function is concave down because my second derivative is negative. You're welcome. All right, let's go. Stand up. Stand up. Let's go. Move around. We got like 2 more to go. 2 more to go. Okay, here we go. Example 4 says, use the concavity test to determine the intervals on which the graph of the function is concave up and concave down. So all we care about is the concavity. We want to know where it's concave up and concave down. So I have the original function. I'm going to take the first derivative. Derivative of 5 is 0. Derivative of negative x to the 1/3 is going to be negative 1/3 x. Then I subtract 1. So that will give me negative 2/3. And now I don't really need the first derivative because they don't ask anything about extrema or increasing or decreasing, anything like that. But I need it to get the second derivative. So I'm going to go ahead and take the second derivative. So negative 2/3 times negative 1/3 will give me positive 2/9 x. Subtract 1, that gives me negative 5/3. So I can write this. I want to write it like this so that it's easier to analyze. 2/9x to the positive 5/3. Or another way I could write that, 2/9 times the cube root of x to the 5th. And they ask about concavity, so I need to check for inflection points. And an inflection point is where the second derivative is 0 or undefined. So looking at this, is my second derivative ever 0? The answer is no, because my numerator is 2, and it is always 2. There's no variable, therefore it can't be 0. However, is f double prime undefined? Yes. At x equals what? What value of x makes the denominator 0? 0. So 0 is my potential point of inflection. And again, I say potential because it's got to change signs. When I say it, I'm referring to the second derivative. So I'm going to check and see if it does change signs by making a sign chart around 0. and plugging my values into the second derivative this time. So let's plug in -1, for example. If I plug in -1 here, -1 to the 5th is -1. Cube root of -1, -1. -1 times -9 is +9 is -9. 2 divided by -9 is, that just seems like a lot of work to get a negative. Yes.
If the negative is inside of a cube root,
It can be negative. We can take cube roots of negative numbers. We cannot take square roots of negative numbers. Okay, those are imaginary. And if I plug in a positive value, that's very simple, right? If I just plug in 1, everything's positive. So this is plus. So I can say now, based off my sign chart of the second derivative, it is going to be concave up from 0 to infinity. It is going to be concave down from -infinity to 0. And I can say x equals 0. X equals 0 is a point of inflection. X equals 0 is a point of inflection because f double prime is undefined and changes from negative to positive. And so let me do one more here. It says in example 5, find all points of inflection of the function. So I need to take the first derivative. I'm going to use my good friend, the quotient rule. Do you have a question?
No.
Okay. So low D high minus high D low over low squared. So I've got x plus 1 times 1 minus x times 1 over x plus 1 squared. And so let me clean this up a little bit. That's going to give me x plus 1 minus x over x plus 1 squared. And now look at my numerator. My x's will cancel, and I'm left with a 1. And I'm going to go ahead and write this for simplicity. I'm going to write this as x plus 1 to the -2, moving that up, because I'm going to take the derivative again to get my second derivative and use my good friend, the chain rule this time. You don't have to, though. So my second derivative is going to be -2 x plus 1 to the -3 times 1. And then I'm going to move my negative exponent to the bottom. So that's going to give me -2 over x plus 1 to the third power. So now I need to check for potential points of inflection. So where the second derivative is 0, and that is never, because it's always -2 in the numerator. However, f double prime is undefined at x equals -1, because if I take -1 and plug it into my second derivative, I'm going to get a 0 in the denominator. So now let me make my sign chart. And this is f double prime, and this is -1. And I'm plugging values again into the second derivative. So if I plug in -2, that's going to give me -1, and -1 cubed is still -1, and -2 divided by -1 is positive. All right, and then if I plug in, let's say 0, that's going to give me 1 cubed, and 2 divided by 1 is going to be negative. So I'm going to say f changes concavity at x is equal to -1. But x equals -1 is not a point of inflection. Why not? Because my second derivative is 0 and it changes signs. So why is it not a point of inflection?
Because it doesn't exist in the original function.
Well, that is a good point. Can you have a point of inflection if the point does not exist? And the answer is obviously no. Look at my original function. What happens at -1? In my original function, there is an asymptote. And so I can't have a point of inflection because there is no point. Okay, so again, just like the critical point has to exist, a point of inflection also has to exist. And so you need to check, just because my second derivative is undefined or 0, and my second derivative changes signs, I still can't say if it's a point of inflection if it doesn't exist in the original function. So I'm going to say because x equals -1 is undefined in f of x.